In this example, we're going to examine what's known as a Poiseuille flow. This is a steady flow of an incompressible fluid through an infinitely long circular pipe. So let's write this out. So a Poiseuille flow, this is named after a famous fluid mechanics person from long ago. And the geometry that this kind of flow describes is we have a circular pipe with a radius capital R, and it's infinitely long in the horizontal direction. Let's put a coordinate system on here as well. So this is the little r direction, and z is the axial direction. And so the pipe is infinitely long, and we're going to assume that it's filled with a fluid, a Newtonian fluid specifically, incompressible, constant viscosity. And we're going to make a few assumptions in the system as well, in addition to what I just described. One other thing, the pipe walls are fixed, so what's driving this flow is a pressure gradient. And the pressure gradient will be dP dz. This is how the pressure changes in the z direction. And for the flow to go from left to right, we need the pressure over on the left side to be larger than the pressure on the right side, so that we push the fluid through the pipe. That means the pressure has to be decreasing as you move in an increasing z direction. So with that less than 0, that means that we have flow in the positive z direction. You can just reason that out just physically by thinking about it. Just imagine you're pushing little bits of fluid, and if you think about pushing the little bits of fluid, you'll figure out that that needs to be negative. Okay, so let's make some assumptions here. This is very typical when we do Navier-Stokes solutions. We make many different, first of all, what we do is define the geometry, and then we make a lot of assumptions in order to simplify the equations enough that we can solve them by hand. So the first assumption we'll make is that the flow is axisymmetric. And there's no swirl component. I'll describe that mathematically in just a moment. Okay, so axisymmetric means that if we rotate the cylinder, the pipe, around this center line, the flow will always look the same. It looks exactly the same with respect to kind of the theta direction here. So that means axisymmetric. And by saying no swirl component, it means that the flow is not corkscrewing down the pipe. There's no theta velocity. So axisymmetric means dd theta of whatever is 0. So that's the axisymmetric part. And the no swirl part means that u theta is equal to 0. Theta, again, is just in the direction kind of going around the center line. All right, so then the next assumption we'll make is that the flow is steady. That means nothing's changing with time, so ddt of whatever is 0, so it's not changing with time. Third assumption we'll make is the flow is fully developed in the z direction. I'll just abbreviate fully developed as FD. Flow is fully developed in the z direction. That means that the velocities aren't changing in the z direction. I don't have to write the u theta one because we already said u theta was 0. So fully developed in the z direction, meaning if you looked at the velocity profile here, and the velocity profile here, or the velocity profile even further downstream, they would all look identical. And that makes sense because if this pipe is infinitely long, there's nothing in here that would anchor down one particular part as compared to another part. It looks exactly the same here as it does there, as it does there. So that means that kind of behavior where it doesn't change with position is called fully developed. And then another assumption we'll make is that there are no body forces. So we don't have to worry about gravity in the radial, tangential, or z directions. You could relax that, for example. You could say that there's gravity in the z direction, but for our particular case, we're not going to worry about that. The flow here is being driven entirely by the pressure gradient. We're pushing the fluid through the pipe. And then assumption 5, we've already said this, is we'll assume that we're dealing with an incompressible Newtonian fluid with constant density and dynamic viscosity. So we don't have to worry about how the viscosity is changing with respect to pressure or location or anything like that. We don't have to worry about any of that. Those are just constant values. Okay, so this again is very typical of how you solve Navier-Stokes problems. You start with your geometry, try to keep it well defined. You make a number of assumptions. Now, these assumptions are certainly limiting, but they're all very reasonable for actual engineering applications. I mean, many flows we deal with are steady. If the pipe is very long, if it's a very long pipe, then being fully developed is actually a pretty good assumption. The flow being axisymmetric, no swirl component, that's actually a very reasonable assumption as well. You know, incompressible Newtonian fluids, reasonable. No body forces, that's fine, you know, especially for a horizontal pipe. So all of these are very reasonable assumptions to make. Okay, so the first thing that we'll do is we'll look at the continuity equation. And this part is not really a requirement to do this. You could one assumption you could make here is to assume that the flow is going in layers, so that the radial velocity component is 0. That could be an assumption, but I'm not making that assumption here. We're going to actually prove that is the case through the continuity equation. So I'll just show you how to do that. So we'll write the continuity equation, and actually we need to write it in cylindrical coordinates because you know, obviously the problem is well suited for cylindrical coordinates. So here's the continuity equation in cylindrical coordinates. It's just conservation of mass for a very small control volume. And then we can go ahead and simplify this. So this term will be 0 because we said that the flow is axisymmetric. That's number 1. And there's no swirl component. So that's assumption number 1. And this last term is 0 because it's fully developed in the z direction. So that's number 3. And I highly recommend that when you simplify these equations, when you set things to 0, indicate why they're 0. So we can always refer back to these assumptions. That'll help both you, when you're working through the problem, to better understand why things are 0, what are the physics involved, and it'll help someone else who's reviewing your work better understand what it is you're doing. So now that we've done that, we'll see that we have this term is equal to 0. And I, of course, can multiply through by the r, so I can get rid of that. And then I can integrate once with respect to the radius. And so then I'll be left with r, ur is equal to a constant. So ur is some constant over little r. Now to find that constant, we need to take a look at boundary conditions. So let's think about this where we need to know where, we need to look at a place where we know what the radial velocity is. So where we know the radial velocity is right out here at capital R. This pipe has solid walls, so there's no flow through the walls. So we know that at little r is equal to capital R, the UR is 0. So no flow through pipe walls means that UR at little r is equal to capital R is 0, and then that just means that that constant has to be 0, right? If I put in a big R here, and this is 0, then the C has to be 0. Well, if the C is 0, that means that UR is 0 everywhere. So you can see that there is no radial component to the velocity in this pipe. So the flow is just going in nice layers. We call this laminar flow. Lamina just means layers. So laminar flow just means it's moving in nice layers. And that came about because we assumed that it was axisymmetric and fully developed, that we didn't have any variations in the z direction or in the theta direction. So that necessarily means that we have to go in nice layers. All right, so we'll call that condition number 6. It's not an assumption, at least the way that I did it here. I didn't make an assumption about it, I just proved it. But if you wanted to, you could also make that an assumption up here in your list and call it assumption number 6, that there's no radial component. You can make that assumption, but again, you don't have to, and I just showed you that you didn't have to here. So we'll call it condition number 6. It's not really an assumption the way I did it, but we'll make use of it in a moment. So now the next thing we do is we're going to solve the Navier-Stokes equation in the z direction. Why the z direction? Well, when you look up at the problem here, all the velocity profile that I'm trying to get is the uz velocity. So it makes sense to look at the Navier-Stokes equations in the z direction. So then we'll have to write that out. And again, we're dealing with cylindrical coordinates, so we'll have to make use of the form of the Navier-Stokes equations in cylindrical coordinates. In cylindrical coordinates, you wouldn't need to memorize those. You can look those up in a table. You can find them on the internet pretty easily as well. Let me write it all out and then I'll describe what it is what we're looking at. Okay, there's a lot to write down there. All right, so let me just describe what we have here. So this is the component of the Navier-Stokes equations just in the z direction. On the left-hand side, we have, it's kind of like mass times acceleration. This term in parentheses is the Lagrangian derivative of the velocity, the z component of the velocity. So this is like the acceleration in the z direction. And the density is like mass per unit volume. So this is mass times acceleration per unit volume. And then on the right-hand side, this is the net pressure force acting on a little piece of fluid. The way you can kind of think about that is imagine you have a little piece of fluid and you have a pressure on both sides, but there's a little bit of a pressure difference. So if this is dz, then from the Taylor series approximation, you can see that we have a little bit of a pressure difference potentially from one side to the other. So this is the net pressure. The pressure P's will cancel out. And what you're left with is the net pressure force acting on, which is just the pressure gradient. So this is the net pressure force acting on a piece of fluid. This term with the mu times whatever's in the square brackets here, this is the net viscous force acting on the little piece of fluid. So that has to do with like the viscous stress on the top and the viscous stress on the bottom. And those are second order derivatives. And you can sort of reason your way to the second order derivatives is because you remember the shear stress is like, let me just write this down here. Remember, like just in Cartesian coordinates, the shear stress is like a du dy, right? So there's just a first order derivative here. But just like the pressure variation here, the stresses between the top and the bottom, you might have a tau and a d tau dy here times a dy. So you can see that the stresses, it's the stress gradient that will matter for the net viscous force acting on the fluid element. So you see that there's a derivative here and then there's a derivative here which will result in a second order derivative, and that's why you see second order derivatives here. So this is the net viscous force per unit volume acting on a little piece of fluid. And then of course this is the body force per unit volume acting on the piece of fluid. So this whole equation is like F, pressure force, viscous force, body force equals MA. That's the MA part's the left-hand side. And it's all per unit volume. So physically that's what the Navier-Stokes equations are. All right, so we have this kind of ugly looking expression here. We can go ahead and simplify it though by making use of our assumptions. So let's go through that. I'm going to shrink this down so we can see our assumptions a little better. There we are. So the first term, that's going to be 0 because we have a steady flow. So that's number 2. The second term is going to be 0 because of condition number 6 we just derived moments ago, where the radial velocity is 0 everywhere. The next one is 0 because of number 1. Oops. 0 because of number 1. That it's axisymmetric and there's no swirl component. The last term is 0 because of number 3, because it's fully developed in the z direction, so the ddz terms go to 0. The next term, dpdz, well, that one is just a constant here, because recall that the way we're pushing this fluid along is we have a pressure gradient. So we'll leave that term alone. That's what's driving the flow. Then we come to this term. Well, this one we have to leave alone. There's nothing in our assumptions that affects this term. So that one we have to leave. The next one will be 0 because it's axisymmetric. So that's number 1. The next one is 0 because it's fully developed in the z direction. That's number 3. And the body force is 0 because of assumption number 4. When you work through these problems on your own, I highly encourage you to follow the same approach. Write down the full equation, and then when you start simplifying it with your assumptions, write down what the values are and why those values are the way they are. So here, there's so many things that are 0, but indicate why they're 0. That way, again, you're less likely to make mistakes, and it's easier to communicate what you've done to someone else. All right, so let's go ahead and rewrite this equation with just these two remaining terms. And I'll bring the dpdz term to one side as well as the dynamic viscosity. All right, so here's where we are. Now this differential equation we need to go ahead and solve. Before I go any further in trying to solve this, let me just say a word about these partial derivatives here. Specifically, let me focus on the uz first. So just in general, the z velocity could be a function of r and theta and z and time, just in general, right? So it could be a function of position, could be a function of time. But we've already said that it's axisymmetric, so it's not going to be a function of theta. We said it was fully developed, so it's not going to be a function of z. And we said it's steady, so it's not going to be a function of t. At best, it's just going to be a function of the radius, r. So when we take these derivatives with respect to r, instead of being partial derivatives, those will be ordinary derivatives. So let me just do that. And while I'm at it, I'll just bring this r to the right-hand side. So we'll have ddr, r duz dr, just written as ordinary derivatives, times r over mu dpdz. Okay, so now we can solve this differential equation. I can bring this dr here to the right-hand side. Let me do that. I'll just do it this way. So I'm left with the derivative there, and then there's a dr on this side, and I can integrate both sides. So when I do that, I'll get r duz dr is equal to r squared over 2 mu dpdz plus a constant, call it c1. I just integrated this term here, and that gives me the 1/2 r squared. And then you get a constant of integration here. Let me go ahead now and divide through by this r, and then solve the last differential equation here. So we'll have duz is equal to r over 2 mu dpdz plus c1 over r, and that whole thing is multiplied by dr, because what I've done is I've multiplied by the dr. I divided through by the r and multiplied by dr, so that's where we are. And then I can integrate both sides of this as well. So then I'll get a uz is equal to r squared over 4 divided by mu times dpdz plus c1 natural log r plus c2. So that's what my general velocity profile looks like. It's kind of this weird parabola with a natural log term in there. So it's kind of hard to visualize. But let's go ahead now and try to evaluate what these constants are. So we'll need two boundary conditions to figure out what the two constants are. So let's think about where we know the z velocity up here. So one place where we definitely know the z velocity is along the walls, right? We have the no-slip boundary condition along these walls, so the z velocity should be 0 there, right? So we can make use of that right away. So no slip at pipe walls. What that means mathematically is uz at little r is equal to capital R should be 0. So I can plug that in, and I'll get that. So if I plug in here, I'll get capital R squared over 4 mu times dp dz plus C1 times natural log capital R plus C2. So C2 is the negative of that whole thing. All right, so that's one boundary condition. Now we need another boundary condition in order to figure out what C1 is. Okay, but I'm just going to redraw the picture here. So we've got our pipe. There's our center line. This is out at capital R here. And then there's our coordinate system. So we've already used the obvious boundary condition that there's no slip at the pipe walls here. It's not clear it's not immediately obvious what the second boundary condition is. But we can figure it out pretty quickly. If you look at this term, the C1 times natural log R, think about what happens to the natural log as R goes to 0. So the natural log, if you plot out what the natural log is as a function of R here, this is natural log of R, what happens is it actually goes off to minus infinity. Right? When R goes to 0, the natural log will go to minus infinity. Now, clearly, we won't have infinite velocities here, right? When you go to the center line, the pipe shouldn't go off to an infinite velocity. If it did, we'd all be in trouble. Like the next time you take a drink through a straw, you have a soda and you take a drink through a straw, be thankful that it doesn't go to infinite velocity along the center line, because then you would basically poke a hole in your head because of the high-speed jet that would follow. So clearly, we always have finite velocities in our pipe flow. So that is actually going to be our other boundary condition, that the flow velocity always remains finite. So what that means then is that the uz will always be finite, so that means that C1 must be 0. Because the natural log of R, when R goes to 0, goes to minus infinity, and we can't have that. So the fact that the flow velocity always remains finite means that C1 has to be 0. Now, another way you could formulate this boundary condition is to actually go back to this step for a moment. Okay, so this one, if you look at this left-hand side, this derivative here, this looks very similar to the shear stress. This looks like a tau RZ shear stress. That would just be mu times duz dr, assuming that there's no velocity in the radial direction. So that's like a shear stress, right? This term right here. If I divided through by r, this right-hand side would be the shear stress if I multiplied it by mu, right? Well, if you look at this pipe, you might realize that, well, the velocity profile in this pipe should be symmetric, right? That because it's axisymmetric, there's no preference for the velocity to have, let me just sketch this out. There's no reason you should have a peak to one side of the center line or to the other side of the center line, right? There's no preference for that because of the symmetry of the problem. So you would imagine then that there would be an inflection point instead right at the center line. So So either the velocity is a maximum at the center line or it's a minimum at the center line. But nevertheless, there's an inflection point right at the center because of symmetry. Now, if you think about that for a moment, what that means is that the velocity right at the center isn't changing with respect to the r direction. So what that means is that the velocity here, the change in the velocity in the z direction with respect to a change in the radius should be 0 at the center line. Because it's symmetric, it has to be 0 there. Does that make sense, hopefully, to you, that the change in the z velocity, as you make a small change in the radial direction, should be 0. You can see it's almost vertical here. So the velocity in the z direction isn't changing as you move in the radial direction. So that means that the shear stress at little r is equal to 0 should be 0 because the slope is 0 there. So if I made that, recognizing that, if I just came to this equation and I made duz dr is equal to 0 when r is equal to 0, then you'd see that I would end up having to make C1 equal to 0. Okay, so that's another way you could formulate this boundary condition. I think it's just easier to see it as the velocity remaining finite, but you could think about it this way as well. Either way, you get C1 equal to 0. All right, well, let's continue on. We now have our C2 value, so we can plug that back in up here and rewrite our equation. So we'll have uz, and if I go ahead and plug in and then just do a little rearranging, I'll give you what the final result looks like. I won't make you suffer through all of my algebra. So let me just give you the final result. So this will be the final result when I plug this C2 back in up into here and then set C1 equal to 0 and then do a little rearranging. It'll end up looking like this. So if you look at this velocity profile, this is actually a parabola. Actually, it's what we call a paraboloid. It's a parabola that's rotated around the center along the center line of the pipe. So if I just sketch this out, you can hear the pipe walls. It's the radius r. Here's the z direction. The velocity profile looks like a parabola with the maximum at the center line. And then you just kind of rotate this around the z-axis and it makes what we call a paraboloid. So the maximum velocity should be right at the center line here. If you plug in r is equal to 0, you can get the maximum velocity, so uz max. That occurs when uz is evaluated at r is equal to 0, r is equal to 0. That'll just be capital R squared over 4 mu minus dp dz. And that's your maximum. By the way, let me just comment again on the dp dz. Remember that we said that if the flow is from left to right, as shown in the picture here, then dp dz has to be less than 0. So this is why I put a negative sign right in front of it here. Because for this picture, dp dz is 0, and then dp dz is negative, and then I throw another negative in front of it, and that just makes it positive. So you can see the uz velocity will be positive then. Okay, if we wanted to find, let's say, the average velocity, the way we would do that is we would just set the volumetric flow rate found using the average velocity. So that would be u bar times pi r squared. So that's just the average velocity times the cross-sectional area here. Remember that this is r, capital R here. So that would be the volumetric flow rate found using the average velocity, and that volumetric flow rate should be the same volumetric flow rate using the actual velocity up here. And the way we find that is we'd have to integrate because the velocity profile changes with respect to radius. So over a little annulus that has an area of 2 pi r dr, if I just draw this kind of end on, here we have a little annulus out at some radius little r. The thickness of this is dr. Over that little ring or annulus, the velocity remains constant, so I can find the volumetric flow rate through that little ring at that radius. The area of that little ring is the circumference 2 pi r dr, so that's where this comes from. So this is the velocity at that radius times dA, so that's the little bit of volumetric flow rate through that ring, and then I would add up all the volumetric flow rates as little r goes from 0 to capital R. So then I could just substitute in this, for this velocity here, I would just substitute this in and do the integral. And again, I won't force you to listen to me go through all that. I'll just give you the final result. When all is said and done here, the average velocity comes out to be capital R squared over 8 mu times the minus dp dz. And that, if you look at that for a moment, this expression looks just like that. It's just they're off by a factor of 2. So the average velocity is actually just 1/2 the maximum velocity. So that's kind of a handy piece of information to have. Another thing that might be of interest is the shear stress at the walls, because you can see here that the walls are holding the fluid back, right? There's a pressure gradient that's pushing the fluid from one side to the other, from left to right, and the walls, because of the no-slip boundary condition, are holding onto the fluid there. So there's some shear stress the walls exert on the fluid. So we could find that. So the shear stress at the wall, of course, would be mu times the stress there that would be of interest to us is the du/z dr stress. So the shear stress at the wall is the same as the tau rz evaluated at r is equal to capital R. That's the shear stress on an R face in the z direction evaluated at the walls, so right all the way out to the sides here. That's just the wall shear stress, so that'll be mu times du/z dr evaluated, little r is equal to capital R. And if you plug in the values for that, you'll get that that's equal to capital R over 2 times dp dz. Or if you want to write it a little differently, it'll actually come out to be minus 4 times mu times u bar over r. The reason I've written it down this way is because we're going to make use of that a bit later in the course when we start talking about pipe flows. In fact, what we'll end up doing when we deal with pipe flows is we'll write out a dimensionless wall shear stress. What I mean by that is we'll just take the wall shear stress and get rid of the units of it by dividing through by the dynamic pressure in the pipe. Remember that dynamic pressure is like a 1/2 rho v squared, but I'm making a dynamic pressure based on the absolute value. I'm sorry, based on the average value of the velocity. So I'm just making this dimensionless. And for historical reasons, people multiply the numerator by a factor of 4. That's just historical. It doesn't change the dimensions at all, but they just put that in there. And then if we take the absolute value of that and I plug in my expression here and simplify, this will come out to be 64 times mu over rho u bar. And then I'm switching to a diameter instead of a radius, because oftentimes we describe pipes by diameters rather than radii. And that, as you'll learn in this term in parentheses, as you'll learn a little bit in just a couple of lectures, that's 1 over the Reynolds number. So this will be 64 over the Reynolds number based on the pipe diameter. So this is just a dimensionless wall shear stress. It's just the wall shear stress expressed in a dimensionless form. Wall shear stress just made dimensionless by the dynamic pressure. And it ends up looking like 64 of the Reynolds number based on the pipe diameter. Again, we're going to come back to, the reason I'm telling you all this is because this will end up being a very important quantity for us when we talk about pipe flows. We call this dimensionless wall shear stress. It's given by another name. It's called a friction factor. Let me just write that down here. This is a friction factor. Again, you'll hear a lot about this when we talk about pipe flows. And the sub D there, there's a name, a fluid mechanics person who this is named after. It's called the Darcy friction factor. That's just the guy's name. So sometimes you'll see a sub D here to indicate it, that it's Darcy. A lot of times you won't see that. They'll just call it the friction factor. But anyway, that friction factor is just a dimensionless wall shear stress, and it's equal to 64 over the Reynolds number, where the Reynolds number is rho u bar d divided by mu. Now, if you looked at the previous example I went through where we looked at a planar Couette-Posay flow, you'll see that in that example, our assumption that the flow is in layers, go all the way back up here, our assumption that the flow is in layers, that there's no radial component, we call that a laminar flow situation. Actually, here we didn't assume it was in layers, we just showed that it was in layers. But it's in layers because we said there was no axisymmetric component and that it was fully developed, so it meant that it had to be laminar. But if you assume that the flow's in layers here, we call that laminar flow, and that really only occurs when this Reynolds number is a relatively small value. So for pipe flows, when the Reynolds number based on the diameter, I'll just repeat how that's evaluated. When it's calculated like that, when that Reynolds number is less than about 2300, the flow is considered laminar. And then when it's laminar, this is a perfectly fine solution. It works really well at predicting what the velocity profile looks like. So that solution only holds when we have this kind of laminar flow, when we have the Reynolds number less than 2300, so that we have laminar flow. If we're above 2300, then we start to get turbulent kind of behavior. And when it becomes turbulent, some of our assumptions break down. We end up getting unsteady flow. It's no longer axisymmetric. It's no longer fully developed. So these assumptions just no longer hold when that Reynolds number is larger than about 2300. When it's below 2300, then it actually works pretty well. Now, why 2300? Why is that such a magical number? We just have observed it experimentally. There's no theoretical justification for that. We just find that that's the case. And 2300 is just an engineering rule of thumb, kind of ballpark number. If you have a very calm, like a quiet laboratory, and you run this experiment and see when you transition from laminar to turbulent flow, if there are no vibrations and you control the air flow in the room very carefully, etc., then the transition Reynolds number may actually be larger. And if you run the experiment in a noisy environment, maybe next to a busy road, it may transition from laminar to turbulent flow at a smaller Reynolds number. But the 2300 is just a pretty good rule of thumb. So this Posay flow solution that we just derived is really only valid when this Reynolds number is less than 2300. Physically, a way to think about why smaller Reynolds numbers result in laminar flow, it'll make a little more sense when we talk about dimensional analysis, but one physical way to think about it is the Reynolds number is actually a ratio of inertial forces that a little piece of fluid would see to a viscous force. You'll see this when we talk about dimensional analysis, but I'm just going to give you a preview here. So the Reynolds number is really like a ratio of a typical inertial force a little piece of fluid sees to the viscous force a little piece of fluid sees. So imagine you have some little piece of fluid here. And when I say inertial force, think about that almost like the momentum of the fluid, that if you push on a piece of fluid, it'll carry for a long distance if it has a large amount of inertia associated with it. So imagine you have some piece of fluid, and let's say we perturb it. We have a flow, and we just give it a little perturbation up or down, something like that, in some flow. If we have large viscous forces, then that perturbation will get damped out, and eventually the piece of fluid will start to go horizontal again, because the viscous forces are dampening out any sort of perturbations. But if we had large inertial forces, and then we perturb it, they're not going to get damped out. They could grow, and this could just end up becoming quite chaotic, right? If we have a large amount of inertia and we're not dampening out the fluctuations, it could just continue. So if you had a small Reynolds number, the perturbations will get damped out and it'll tend to flow just in layers. It'll be a laminar flow. Whereas a large Reynolds number will start to become more seemingly chaotic in behavior, and that becomes more of a turbulent flow. So that's kind of a quick and dirty way to physically get a picture behind why smaller Reynolds numbers result in laminar flows. Okay, so we'll end up referring back to this velocity profile, this Posai flow, when we talk about pipe flows. You can imagine that flow through a circular pipe. It has a lot of practical significance. And when we refer back to this, we're going to frequently refer to the average velocity, the flow rate, and we'll also deal with this dimensionless wall shear stress. That'll be an important quantity. So that's why I give you a preview here, and we'll come back to it again. And then, of course, the Reynolds number will be important as well. We just need to make sure that if we're using this solution and anything derived from it, we need to just make sure that our Reynolds number is in the correct range. Okay, so hopefully the solution methodology here, where we've gone through making a bunch of assumptions about the flow, making use of the continuity equation, and then simplifying the Navier-Stokes equation and doing the resulting math, and then also the boundary conditions. Hopefully all that makes sense to you. All right, we'll go ahead and end it there.